So yesterday I was talking about some of these rules for integrals that we might have used a little bit already, but these are the important rules for integrals that we want to sort of just know and have memorized. First one being, if you have a constant times a function, you can pull that constant out outside of the integral. So the integral from a to b of a constant times a function equals the constant times the integral of the function. So that's a good rule to know. And then if we have two functions being added together within an integral, we can separate that into two different integrals or subtracted. We know that the integral from a to a, or from 7 to 7, or -2 to -2, where there's no interval, that integral is 0, right, because there's no area underneath that curve. And we can flip the limits of integration and put a negative sign out in front. And also, if we have the integral from a to b of a function plus the integral from b to c of a function, that should be equal to the integral from a to c of that same function. Good or no? So these are rules we need to know. Everybody good with those rules, or anybody have questions on those rules? All right. Let's then see if we can quickly apply them to two continuous functions f of g with these three given integrals. So first off, what should the integral from 2 to 2 of g of x be?
0.
Should be 0, right? What about the integral from 5 to 1 of g of x? That ought to be the opposite of the integral from 1 to 5 of g of x dx, which should be
-8.
Oh, g of x, yeah, -8. I looked at f of x. -8. Good? Everybody good there? According to the rules, this 3 can just get pulled out front. This should be 3 times the integral from 1 to 2 of f of x dx, which should be 3 times -4, or -12. And what about the integral from 2 to 5 of f?
Should be the integral from 1 to 5 minus the integral from 1 to 2. So
Good.
10.
So 6 minus -4, which should be 10. Everybody good there? And the last one, the integral from 1 to 5 of f minus g ought to just be the integral from 1 to 5 of f minus the integral from 1 to 5 of g. So 6 minus 8, or -2. Good or no? I will post up some practice problems like those, but I think those are pretty straightforward. They do like to put like one of those on the AP test, though, usually in the multiple choice, of which none of you got to see last year since you didn't have a multiple choice section. So, everybody good with that, though?
Yeah.
All right, cool. So now we're going to get into the beginning of these techniques for integration that are not just integrating using the rules. This one is one that we did talk about last year. So suppose I have something like sine x times e to the cosine x dx. What do I need to do with this to integrate it? Anybody remember or no?
You need a du.
I need to turn it into terms of u. We need to do a u substitution and get a du. So what is our u value going to be?
Cosine x.
Cosine x. Did you say sine or cosine? I couldn't hear.
Cosine x, because it's
Cosine.
nothing else.
So we want u to be cosine x. And so if we go in here and try to write this as sine x e to the u dx, obviously that's a problem because we've got sine x and we've got e to the u, so we get different variables, plus we have a dx, so we have to have everything in terms of x to integrate in terms of x, or we have to turn this dx into a du and have everything in terms of u. And so we want to turn it all into terms of u, since in terms of x was not just one of our basic simple rules. So if u is cosine x, that tells us that du is negative sine x dx if you differentiate cosine. And so all we have to do is put in, I don't know why my toolbar is not showing up today. All right, sorry about that. So we want to get a negative sine x in there, so we can put a negative in, which means we would have to cancel that negative out with another negative sign, which we'll put outside. So we have the opposite of the integral of now e to the u, and negative sine x dx is du. So we can just make this negative integral e to the u du. And whether this negative sign is outside the integral or inside the integral, it doesn't really matter. And we can just integrate e to the u, and we end up with negative e to the u plus our constant. And if we wanted to rewrite this without these brackets, we could just write it negative e to the u minus a constant, but minus a constant and plus a constant is effectively the same thing because that constant could be any value we want it to be. So we'll just call this negative e to the u plus some constant.
Should we put our answers when we do u subs in terms of x or u?
Oh, right. Sorry. So negative e to the cosine x plus a constant. Yeah, always convert back. I don't know why I didn't convert that back just now. Always convert it back. Good or no?
Great.
Spectacular. Let's do another one. The integral of x squared root 5 plus 2x cubed. So generally, whenever we do these u substitutions, we want u to be the interior of some other function. Right, so it's kind of like what would be in the parentheses of the more complicated part of it. So it's going to be this u equals 5 plus 2x cubed. Okay. So if u is 5 plus 2x cubed, what is du going to be?
6x squared dx.
6x squared dx. We have an x squared. We just need to turn it into a 6x squared by putting a 1/6 outside and a 6 inside. And then we can take the 6x squared dx and replace it with du. So we end up with 1/6 the integral of u to the 1/2 du. And that becomes 1/6 of 2/3 u to the 3/2 plus our constant. And I'm going to just call that constant 1 there, just for fun. And when I distribute the 1/6 then, this is going to give us 1/9 of 5 plus 2x cubed to the 3/2 plus a 1/6 of our constant that we have. 1/6 of the constant is just a constant. Good or no?
In what future class would numbering the constants and keeping track be important?
In what future class would that be important?
Or doing what?
I mean, it's important all the time to sort of keep track, but not really for any of these. It's important if you're doing an indefinite integral, it doesn't even matter at all in the least ever. But if you're doing a definite integral or you're trying to solve a differential equation, if you're doing a definite integral, that wouldn't matter because there's no constant. But if you're trying to solve a differential equation, it does matter what's your constant. You know, when you go from a constant to a 1/6 of that constant, it matters when you try to solve for the constant is the only time it really matters.
Oh, okay.
Or if you're trying to see if your answer is equivalent or differs by a constant from some other answer that you might get for an integral, because as you'll find out later on in this class, sometimes the constant that I get might be very different than the constant you get within our different integrals for a question that we're both working on. It's the same question. So short answer, it doesn't really matter at all. Long answer, pay attention to it, but only when you have to solve for that constant.
Okay, cool, thanks.
Yeah, I mean, for our purposes, it's not really going to matter at all. When you get into a differential equations class, which you normally take after you've taken the third semester of calculus, that's really when you end up doing a fair amount of stuff with the constants and all that. So.
Okay, cool, thank you.
Mm-hmm. All right. Any other questions on that one? Everybody good with that?
Good with that.
All right. We got an integral of cotangent of 7x. So before we do this one, in fact, I want to go back here. Let's just do an integral of cotangent of x. How do we integrate cotangent x? Without having just memorized the formula. How do we do the u substitution for it?
You can do cosine over sine, and then you have to do something.
All right, so what's our u going to be? How about sine x? And our du will be cosine x dx. And so this ends up becoming an integral of du over u, which is natural log absolute value u plus our constant, or natural log absolute value of sine x plus our constant. This integral right here of cotangent, you're going to want to memorize. I recommend that you memorize it. If you don't memorize it, that's fine. You may just have to go through and do this process to find that integral every time. It'd be nice to just know it. Okay. Everybody good with that integral using a simple u sub there?
Yes.
Okay. What about an integral of tangent x dx? We also want to know this one. This would be an integral of sine x over cosine x dx. And if u equals cosine x, then du would be negative sine x dx. So we would want to throw in some negatives there. And we'd end up with the opposite of the integral of du over u, which would be natural log absolute value, negative natural log absolute value u plus our constant, or negative natural log absolute value cosine x plus a constant. Or if we wanted to, we could also call this natural log absolute value secant x plus a constant. And so those are our antiderivatives of tangent, negative natural log absolute value cosine and natural log absolute value secant. Either one of those would be good. I would recommend that you memorize those as well, in addition to all the other integrals that you should memorize. Both of those come up often enough that it's nice to just know what they are. So, good or no?
Good.
All right, so now that we know what the integral of just cotangent is, we should be able to do the integral of cotangent 7x pretty easily. We'll let u equal 7x, and du will be 7 dx. And so we'll have to put a 1/7 outside and a 7 on the inside. And then this just becomes 1/7 the integral of cotangent u du. And what's the integral of cotangent u? Should be natural log absolute value of
Sine x.
sine of x plus our constant. Good or no?
Yeah, good.
All right. What about this one? This is just an integral of
secant squared 2x.
secant squared 2x, which means u is going to be 2x and du is going to be 2 dx. So 2 and a 1/2, which is going to give us 1/2 the integral of secant squared u du. Or 1/2, what's the integral of secant squared?
Tangent.
Tangent, and tangent u is just tangent to x, and we'll add our constant in, and it should be good. So these simple u subs where it's like a 2x within this trig function that we know how to integrate, or same thing like the 7x in here, or let's say something like an integral of e to the 1/2 x dx. Let's do this one real quick. What would u be? U would be 1/2 x, right? And du would be a half. So we'd end up with 2 times the integral of 1/2 e to the 1/2 x dx, or 2 integrals of e to the u du, or 2 e to the 1/2 x plus a constant, right? These fairly simple ones that are just like one-step u substitutions that are pretty easy ones. You really are going to want to practice those and get good enough at those that you can just do those all in your head. So that when I just ask you what's the integral of e to the 1/2 x, you're just going to tell me, oh, that's 2 e to the 1/2 x. Or if I say, what's the integral of e to the 5x dx, you'll just tell me that that is what?
1/5 5x plus c.
1/5 e to the 5x plus c. Okay, so these very simple u substitutions, you want to be able to get to the point where you can just do those ones in your head. Because when we start talking about this thing called integration by parts, which we will start talking about most likely on Monday, you're going to have to do a lot of these little integrals, and it's going to make life a lot more difficult if you have to write out that u substitution each time. So life will be much easier if you don't have to. Good or no?
Glorious.
Spectacular. All right. What about this one? What should we do?
Would you use sub twice?
Well, what do you want to use sub for to begin with?
3x.
Okay, so if u equals 3x, then du is 3 dx, right? And so we'll need to put in a 1/3, and we'll need to put in a 3, which is going to give us 1/3 of the integral of cotangent squared u du. So I don't think there's going to be another u substitution here because this is cotangent squared. So if you try to do that as like a cosine squared over sine squared, there's no good u sub for that. In fact, there's not really any good u sub for cotangent squared. We're going to have to do something else with cotangent squared in order to integrate this. Anybody have an idea on that? Somebody said something in the chat. Yeah, cotangent squared is equal to cosecant squared minus 1. So we've now got 1/3 times the integral of cosecant squared u minus 1 du. And if we integrate that, what's the integral of cosecant squared u?
Negative cotangent?
Yep, negative cotangent u minus u plus our constant. And if we go in and distribute the 1/3 through here, we're going to end up with negative 1/3 cotangent 3x minus 3x times the 1/3 is just going to be minus x plus a constant. And I'll just call that constant 1 again. Half the time, I'll probably forget to call this some other constant, and it doesn't really matter if you do. It's not a big deal. Good or no?
Do you not need to distribute the 1/3 to the u of the x? Wait, no, never mind. Sorry, it's never mind. I just
Yeah, remember u is 3x, so I did. Yeah, just did it all in one step there. Everybody good or no? All right, let's do another one. Cosine cubed x dx. How are we going to deal with this one? Any thoughts?
You can split it up to cosine squared times cosine and do something like that.
All right, cosine x times cosine squared x. What good does that do me?
Power reducing formula.
Oh, God, we could do the power reducing formula, but God, I don't want to do the power reducing formula. Not today. I want to do something easier than that.
1 minus sine squared, and then
Cosine x times 1 minus sine squared x. Okay. What good did that
and
do?
then u would be 1 minus sine squared x.
No. No, u would be
Sine, right?
just sine. Don't make things more complicated than they have to be. If u is 1 minus sine squared x, then du is negative sine 2x or negative 2 sine x cosine x, which is not.
Oh, okay.
But if
okay,
u
okay.
is sine x, then du is cosine x dx, which, bam, already right there. So this just becomes an integral of 1 minus u squared du, and 1 minus u squared is very easy to integrate, right? U minus u cubed over 3 plus our constant, or sine x minus sine cubed x over 3 plus a constant. Good or no?
Affirmative.
Great. We're going to do, not today, but another day, sometime next week, hopefully, if we get to it. We're going to do a bunch of ones with these trig functions in them. We're going to do powers that are even powers and powers that are odd powers and having multiple sines and cosines or secants and tangents in there. We're going to learn a bunch of rules for how to make those integrals fairly easy. But for now, we'll just do this nice easiest one. We won't worry about any of those other ones yet. Well, I guess we'll do this one, which is a definite integral, but this one should be pretty straightforward. And we're going to actually look at this one 2 different ways because we got 15 minutes left and only one more problem after this. So what should we do with this one? The integral from 0 to pi over 3 of tangent x secant squared x.
You can make it secant x tangent x, which we know the integral of, and then times what's left over? The extra secant x?
Yep.
Can't we just do a U sub?
Yeah, we're going to have to do a U sub. So I assumed that was a truth talking, right? I assume that was a truth's way of saying let's do a U sub with secant x and tangent x in some way, or secant or tangent or something.
Yes.
Yeah, I knew that's what he was going to say. So what do you want your U sub? Who was the second person that was talking?
I think if you made it secant x, then you would already have du in there.
Okay, u could be secant x, and du would be secant x tangent x dx, which we have, right? If I get rid of one of these secants as my u, then I have secant x tangent x left. So this becomes an integral of just what?
Just u du, right?
Just u du. Although we do have to do what? Anytime we have a definite integral and we do a u substitution, we need to convert these x values of 0 and pi over 3 into u values. So if x is 0, what is u? It's the secant of 0, which is what's the secant of 0?
Just 1.
Just 1. And what's the secant of pi over 3?
2.
2. So this now just becomes an integral from 1 to 2 of u, right? Which just becomes u squared over 2 from 1 to 2, which becomes what? 2 minus half or 3/2. Real quickly, just for the heck of it, if we didn't have a definite integral here and we'd integrated this and we got u, right, we'd end up with u squared over 2 plus a constant, yeah? Which would be secant squared x over 2 plus a constant. Just want to make a quick note of that. Yeah?
Yeah.
Everybody good with that? Okay. Oh, that's not what I wanted to do. There we no, that's also, I just want this writing. Why is it, what is going on? No, that's, never mind. All right, I guess I can't move that somewhere else. All right. We've done all this great work here. Woo. All right, let's do some more work on this one. Couldn't we have done a different u substitution for this?
You can do tangent.
Couldn't I have said u is tangent x and du would then be secant squared x dx, which would have given us an integral of u du, wouldn't it have?
It would have indeed.
And tangent of 0 is 0, so that would have been 0. And tangent of pi over 3 is what?
Root 3.
Root 3. So we would have had an integral from 0 to root 3 of u, which, well, hopefully it better come out to be 3/2 still, yeah? Let's see, that should be u squared over 2 from 0 to root 3, which is, well, that'd be 3/2 minus 0, or just 3/2. True? So on one end we got 3/2, and on the other end we got 3/2. But what if this hadn't been a definite integral? What if it had been an indefinite integral? Our integral here would have been u squared over 2 plus a constant, which would have been tangent squared x over tangent squared x over 2 plus a constant. True? And we can see that if this had been a definite integral, we've got a little bit of a strange thing happening here, that although the definite integral came out to be the same, our indefinite integrals certainly don't look very similar, do they? I mean, tangent squared x over 2 and secant squared x over 2 are not the same thing, are they? So if this had been just a definite integral without the 0 and the pi over 3, which one of those answers would be right?
Well, maybe like the C part is different depending on which like route you take.
Exactly. So tangent squared x over 2 plus a constant. What's tangent squared equal to? Tangent squared is the same as 1 plus, sorry, that's not right. 1 plus tangent squared is secant squared. Let's do this the other way. Secant squared x over 2 plus a constant. Secant squared is equal to 1 plus tangent squared, isn't it?
It is.
And this would then be 1/2 plus tangent squared x over 2 plus a constant. So this is where these values of these constants start to matter a little bit, because constant plus a half is just some other constant, isn't it? And so we could then say that this is the same as tangent squared x over 2 plus some other constant. And so while these are not the same, they differ by a constant. And it's okay if two integrals differ by a constant, right? Because it doesn't matter what that constant is. It can be any value that we want. And so if we got the answer of tangent squared x over 2 plus a constant, that constant is greater by 1/2 than the constant if we'd gotten secant squared x over 2 plus a constant. You guys see that?
Yeah.
Cool. And so oftentimes, I mean, you know, I could have just given you this problem, not this problem as a definite or as an indefinite integral on the quiz, and some of you would have got this answer, and some of you would have got this answer, and you would have all been right, right? But it's good to recognize that there could be multiple different things that when you take their derivative still give you this function.
Would there ever be a time where one route is more advantageous than the other?
I mean, sometimes the substitutions or whatever other integral rules that we're going to be using soon next week might be easier than the method might be easier, but no, for our purposes, not really. No, nothing is going to matter. It's not going to really matter which way you do it or which answer that you end up getting, other than if you have to like try to evaluate it in some way, it might be easier with one integral than the other, but there's no real way of knowing which one is a better solution. And most of the time, there's no answer to which one is better. Does that answer your question?
Yeah, thank you.
That was the long answer. The short answer is no, it doesn't matter. All right. Let's do another one of these. And I'm going to throw one more problem up because I think we'll have time to do it. But let's do this one first. How are we going to do this one? That's right, I use substitution. What should you be?
X
Better at math? Sorry, what'd you say? I was like,
X squared.
minus the 4. Let's do x squared minus 4 with du equal to 2x dx. We need a 2 up there. We need a 1/2 outside. So we got 2x dx over x squared minus 4, which then allows us to make this 1/2 the integral of du over u. But our limits have to change. Right? This was still 0 to 1. But when I change it into u, it becomes -4 to -3. So we end up with 1/2 natural log absolute value u from -4 to -3, or 1/2 natural log of 3 minus natural log of 4, right? The absolute value of your -3 and the absolute value of your -4. And this answer would be good. We could also write this as 1/2 natural log of 3/4 if we wanted. We could write this as 1/2, no, not 1/2. We could write this as natural log of the square root of 3/4. We could write this as natural log of root 3 over 2. I'd accept any of those. If it was a multiple choice question, you should be able to get any of those out of it and see that as an answer choice. Good or no?
Wonderful.
Great. All right. Let us then do one more problem since we still got 4 minutes here. And I hate to let you go early on a Friday. Let's integrate. How about x to the 5th root x squared minus 1? dx. What should we do with this?
Make x squared minus 1 u, and then divide x to the 5th into a couple parts. And then
All right,
maybe
so
like,
first off, let's get our du, which is 2x dx. And then you're saying, since we've got an x in here, but we also have another x to the 4th, rewrite it as a 1/2 and a 2x with an x to the 4th in there. Is that what you're saying?
I think so.
Yes would be a great answer right now. Yes, that's exactly what.
Yes, that's definitely what I was thinking. Yes.
Yeah, nice. That's exactly, because the 2x dx can become your du. So we're going to have a 1/2 of an integral of u to the 1/2 du. But we've still got this x to the 4th term in there. But we know what x squared is. X squared is u plus 1. So x to the 4th ought to be u plus 1 squared. And so sometimes it's okay to have a little extra piece in there as long as we can, in our original u substitution, solve for that piece and substitute it in terms of u. Everybody good with that? Okay. So from there, we will just distribute out the u plus 1 squared with the u to the 1/2. And maybe I'll throw the 1/2 in there with it also. So the u plus 1 squared is u squared plus 2u plus 1 times the u to the 1/2. That's going to give us a 1/2. If it's u squared times u to the 1/2, that's 1/2 u to the 5/2. And then the 2u that's in there, it's going to get multiplied by the half to become a u times the u to the 1/2 is going to be u to the 3/2. And these are all still inside an integral. And then we have the 1 u to the 1/2, and so it's 1/2 u to the 1/2. Everybody good with that? Or no? You guys good or no? Yeah?
Yeah, good.
Okay. And so now we'll just integrate. So this becomes u to the 7/2 times 2/7, and half of 2/7 is 1/7. So it's u, or x squared minus 1 to the 7/2. And then plus, this one will become 2/5 of u to the 5/2. And then this one will become 2/3 u to the 3/2 times the 1/2, which is 1/3 u to the 3/2 plus our constant. Everybody good there or no?
Yeah.
Spectacular. So that is, let's see, what did that take us? Did that take us 3 days with a quiz in there? 3 days with, I think, 2 quizzes in there for us to get through what would normally be like a 2.5 to 3 week integral unit in AB, if this was AB. So that's all the AB integral stuff. Now, starting on Monday, we are going to slow down a bit and do a lot of extra practice with some integrals that are going to get quite a bit more difficult, and a bunch more rules, a bunch more specific integrals you need to memorize, and a bunch of techniques that we're going to have to learn. So from here till winter break, and probably the first week after winter break, it's going to be a little slower and a lot of pretty much all new stuff. So that's where we're at. I will post up some homework that will be due at the end of the weekend. And other than that, I think we're good. Anybody have any questions?